So I'm going to give a very simple introduction first to machine learning, why we are here. Okay, and then I'm going to talk about supervised learning, nothing new there. And then unsupervised learning and reinforcement learning that might be new to some of you. Okay, and that's where do I want to go there. Okay, and I like to start with this. I don't know if you, probably most of you are very young and didn't read this report. It's an amazing report that the Obama White House did in the last month of it came out in December 2016, and it explains why machine learning and AI might change the US economy and overall the rest of the economy. You need to look for it in the dark web because the current administration didn't keep it. I don't know why, but any guess would be good. And basically what you see is economists looking at AI, the machine learning algorithms are going to change. And then they give a very good example of what self-driving cars might mean to the US economy. Only from the driver's point of view. They don't talk about insurances. They don't talk about dealerships in cars. They don't talk about police. They don't talk about judges, because there is a big part of the US economy in which all of those people deal with traffic offenses. Okay? So in any case, it's a very good report to have a look. Okay? And I had a very interesting video here from the Royal Society. Fingers crossed, because I don't know if we will have sound. You will have sound good? Okay. So this is, you can share with your family when they ask you what you're doing. Okay. I think it's an excellent video, even for us, because if you look, basically the three problems that they talk about being a problem will be important in AI from comms. Okay, we will need to transfer what we learn in one communication system to another. We will need to learn abstract concepts, maybe things that we didn't see in the signal. We saw that in the previews, and especially watching learning. Okay, many of these algorithms require too much data, and it will take too long to train a model every time, starting from scratch. So those are problems that we still need to solve, and in where comms might be the way to go. Fairness will be also another thing that might be interesting in comm if you start looking at network traffic and start assigning resources due to network traffic, and you might give it to the people that needed the least. So that will be also, if you are talking about that higher level, that might be an issue for us. Okay. The other resources that you see in here, there are some self-driving cars from Google. In case you didn't like the previous one by Tesla, there is another one by, and then the shopping by Amazon in Amazon Go. That is also very cool, a cool video. I'm lazy, but not that lazy. I'm not going to go through all the videos today. Okay. So why we talk about machine learning and why I don't talk about artificial intelligence? Okay, that is a big difference. Okay, and there is a big fight between how do you see it. For me, artificial intelligence, the difference is a top-down approach. Human is the center, and what we're trying to do is imitate human. These are the definitions that you have in that artificial intelligence book, and what is the goal? And the goal is always to mimic humans. Okay, machine learning, and this is just the cover of the machine learning book that I like. If you haven't read it, go ahead. This is a good time. The definition in machine learning is simpler. The goal is, I have data. What can you tell me about that data? Okay? There is no human in the loop. We're not trying to mimic human. The only thing that we have is we go from data to a model. Okay? And that's the whole point. So both then artificial intelligence and machine learning are very different. I mean, artificial intelligence is a top-up. You have humans. How can I look at humans? And then we come up with things like human-like behavior, and then we have something like logic and search and rule-based approaches. All these things that in the 80s keep on failing over and over again. Okay? In machine learning, it's much simpler. It's a bottom-up. We start from the data, and from that data, we're going to feed a model. And we hope that that model is useful. Okay? Always remember what Cox says. All models are wrong, some are useful. That's where we're trying to go. Okay? Where both are connected is with learning. Many of these things try to use learning not in the psychological sense, but in the sense that we go from data to fitting parameters. Okay? And that's more or less what the difference between both of them. I'm going to be talking mainly about machine learning. What is supervised learning? Supervised learning is simple. It's a simple problem. Okay. The idea basically is we already know what's the solution to the problem. Okay. The only thing that we're trying is to automatize it. Okay. So basically, we have a few images of A's, and somebody tells us that those are A's. We might have some images that we're uploading to Facebook. Okay. And then you upload that image, and then Facebook tells you it's a valid image. You avoid that other image, and then they tell you it's a valid image. I didn't dare to put an invalid image because Facebook, the only thing that they're doing is checking for porn. So I didn't want to get into trouble here.
So here is you show a picture of a leader, and then people have to recognize Obama afterwards?
No, the thing is, well, the only thing that I have in here, and Elizabeth, you said thank you, is that this is a valid picture that I can upload to Facebook. Okay, that's the only thing that I'm going. But you can even do more. You can go and say, hey, Google, if I give you an image, what is the label that you will assign that image? Okay, so you upload this picture. I tried yesterday, and you get go. Okay. All right. So that's also supervised learning, and then it gives you other picture of those. Okay. So basically, the only thing that it does is your supervised learning algorithm in this case will be an image plus a label. Okay. It's good that, for example, it didn't find you. So it means that you don't post a lot in Facebook or you don't post a lot in social media. If you have a big profile, it might find your name in there too. Okay? So it means that you are secretive enough about your life. Okay? The Obama, I also have it because when I started giving this talk the first time around, it's a very good to know that it gets a very wrong label. Okay, because this is one of the problems that you have, and it's very difficult for a human. It's very easy to interpret this image. Okay, for a machine, still we are not there. Okay, because basically Obama is playing a prank on the guy that is waiting himself by stepping on the scale. So you see that, you see all the other Secret Service guys laughing at it. So it's a very good one. There are no machine learning algorithms that is going to give you the right label for them. It might find Obama. It might tell you that this book is in some other guy's book that was published before, but it doesn't tell you the essence of that image, which is Obama playing the prank on the staffer. Okay. One of the things that is important is machine learning models are extremely simple. Okay, we don't do anything complicated. Okay, although Jacob will try to make it hard this afternoon, but. Okay, so the only thing that we do is we have data. We assume that is IAD. Okay, we have training data. We have the input, which we typically call X, and Y, that will be the label. These A's, these valid images, or this label assigned to each one of the images. And then the only thing that we do is, given that we have a model that depends on some parameters, I'm going to estimate those parameters from the data. That's the only thing that we do. Okay? If you're Bayesian, we do the same thing in a complicated way. Okay? What we do is, instead of saying I want to estimate the value, I want to estimate a posterior probability of the value. That's what this P of Y is. And the inference, instead of doing that optimization, we do an integral. This is why Bayesian is complicated. People that are frequentists do optimization. People that are Bayesian do integrals. Integrals are harder than optimization. That's what is more complicated. Okay? And then, in order to do those predictions, we integrate the posterior with the likelihood. Okay? In this slide, what I'm trying to show is why we are here. Okay? If that hadn't happened 10 years ago, we wouldn't get funded for this project. Okay? Or something similar. This one shows when deep learning showed that it could solve a problem that humans couldn't solve before, or that with typical solutions in machine learning we couldn't solve before. Okay? The issue here was, in the ImageNet competition, humans using standard methods in computer visions plus good algorithms in machine learning were stuck in 25%. Okay? For 3 years, they were getting exactly the same error value in the ImageNet competition. Okay? Basically, they were training with SIF features and then a nearest network, SIF features by SVM, SIF features by random forest. All of these algorithms were stuck in 25%. And then AlexNet in 2012, they went down from 25% to 15%, okay, using deep learning. Right after that, on the following year, everybody used deep learning. And now basically they are on human level performance. So when they say, look, in the ImageNet we have human level performance. What is human level performance? One grad student that looked at 1,000 pictures from ImageNet, then took a test with a few images and got a 4% error. Okay? So when they tell you that it's human level performance, is one human with limited training and with limited testing. Okay? So there is no real human comparison. The good thing is you can do this very, very fast. Okay? And that is what changed everything. Is where deep learning became part of the conversation, not only in conference like ICML or NIPS, but also part of the global conversation with everybody. Okay? And that's why we're here, and that's why everybody wants to apply deep learning to communications problem. Okay? We will go back to that at some point. Okay? And this is basically the evolution that we have in deep learning. This comes from the deep learning book. Basically, it's the first or the second figure in the book, and this is basically what we have. This is rule-based system. The white boxes, it means that it's something deterministic or an input. The shaded boxes are the ones that are coming from learned data. Okay? So basically, this rule-based system is what typical AI would do. I will ask a human, how do you classify this image? Oh, I see a dog because of this, this, and this. We write that in a computer program, and then it fails miserably. Okay? The next thing is basically the classic machine learning algorithms is we do features. We look for features in the data. We are smart enough to find those features, and then we apply a shallow classifier there. And we are very good at doing those things. Okay? Random forest, SVN, Gaussian processes, they are all as good as any of them. Okay? Some of them have easier parameters to tune, but they are very good at that. But if we don't get the features right, we don't solve the problem right. What representation learning or deep learning is doing is, oh, humans were horrible at finding features, let's train the features too. Okay? And that's the whole point. Getting the right features for the top classifier to be able to do that correctly. Okay? Then, do we expect another column in this plot at some point? And the answer is yes. Because these boxes that are learned, there is a lot of thinking of what it goes there. Okay, you're going to put convolutional neural networks or RNNs or LSTMs or whatever makes sense for you to solve that problem, and that depends on the problem that you're trying to solve. So if you're trying to solve an image, you're going to put a CNN. If you're trying to put some kind of voice or text in which there is some fluidity in the information, you're going to put an LSTM. What happens if you don't know what your problem requires? Right? Can you learn the structure of your neural network? And that will be the fifth column, and that's what AutoML is trying to solve these days. Okay? And I'm going to go fairly fast here because this is what Jacob is going to cover. The only thing here is to show that a multilayer perceptron is very simple. Okay? It's a linear, it's an scalar product and a non-linearity. Okay? And the non-linearity, what it does is if you're above 0, you leave it as it is. If you are below 0, you threshold it at 0. The non-linearity is necessary because that's the only way that you're universal. If you don't have a non-linearity, the solution is not universal. Okay? And this is just to show that we are doing nothing new. Many people forget about LeNet 89. This is the first LeNet in which they were trying to do digit recognition. They started with digits that were in the MNIST. It was subsampled to 16 by 16 pixels. They only used 2 convolutional neural networks and 1 fully connected. Okay? If you look at that, that's basically the structure of all the other neural networks. The only difference is that we have bigger computers now. Okay? This is the LeNet 5. It has another fully connected and another convolutional. This is AlexNet, the one that we talked about that won the ImageNet competition. It has 6 convolutional and 3 fully connected. No, 2 fully connected. and this is GoogleNet, and then there is one with 100 layers that I didn't fit on the slide, so I didn't put it. Okay, so we are getting to a point in which this is extremely deep. Okay, also we're getting to a point in which we just do it because we can. Okay, and that's one of the things that you should be able to avoid. Don't do things because you can. Do those things because they make sense. Okay, I'm going to talk now a little bit about unsupervised learning. This is before chapter 42 in David Mackay's book, which is, if you haven't read it, I fully recommend it for you to read it, because it's a great book about before the hype of machine learning. Everything is very clear and very good. And the good thing about this thing is supervised learning is only regression. Okay? That's the only thing that we're doing. And supervised learning is the one that is interesting. Okay? And I still agree with Robert. I'm amazed that it works. Okay? Because we're giving nothing and we're expecting to get something out of it. I mean, we saw it in the previous talk that what the idea is, we bring some very high dimensional with a lot of data, and we expect that to go to a lower dimensional that means something to us without telling the machine what we were looking for. Okay? And that is where many of the contributions that you can do might be here too. Okay? Not just try to use supervised learning, but try to use unsupervised learning. Trying to understand what is going on your communication system or your communication program. Okay? Okay, what do you see here? Anyone?
Maybe an arrow. Maybe an arrow.
An arrow. Something else? Not enough coffee? Not enough sleep?
An airplane.
What?
An airplane. An airplane.
An airplane. Good. 15 random points? Anyone? Okay.
It's a runner.
They are random. If you believe
runner,
random.
Runner, like this, runner.
No, it's no. There are 15 random points. If you believe what a computer will give you 15 random points, those are those. Okay? So the issue with these algorithms is that sometimes you see things that are not there, and you have to be able to see those things. This is a picture from yesterday after dinner. Okay? We were all seeing a face and not what it is. Okay? So this is the problem with humans, that we tend to see things that are not there. Okay? The idea of unsupervised learning, the simplest thing is density estimation. Okay? The idea that we're trying to understand is a density. Density estimation is the hardest problem that you can solve. Okay? The estimation of a density in a completely unparametric way is log n in the number of samples that you have. Okay? So as painfully slow as it gets. Okay? If you have a parametric form, then things become a little bit easier, and that's basically what we're trying to do with maximum likelihood. Okay? The most interesting way in which we do this in a parametric form in machine learning is with what we call latent variable models. Okay? And the idea of latent variable models is based on this definitive theorem from the 30s that tells you that if you have data points that are exchangeable, okay, that means that you can, doesn't matter the order that you have those data points. The correlations that you see in the features between those data points can be explained by a latent variable that you do not know. And if you were to know that latent variable theta, you condition on that, the data points are independent. Okay. Let me give you an example. The example of the four PSK that we had before with the 4 points there. Okay. If you see only those 4 clouds, there is a dependency between the samples that you are seeing. If somebody tells you that, oh, that's actually 2 bits that I'm transmitting, then the only thing that you have is for each one of them coming from an independent Gaussian, and the samples will be independent. Okay. If you're able to do that in an unsupervised way, then you know that those 4 points that you have are the 2 bits that you're transmitting. Okay. The same thing you could do if you have cancer patients, and this is the genome. Okay. You can understand that, so theta will likely be the place where the tumor is coming from. And that might be important because sometimes you find metastasis but not the original tumor. So if you analyze the tumor and you say, oh, I took this from the lung, but it's actually a tissue that is coming from the brain, what you have is brain cancer, you don't have lung cancer. What you have is lung metastasis. Okay? And that happens many times because the tumor might realize on the metastasis and not on the original tumor. Okay? When you look at this structure, all of the unsupervised learning algorithms that are out there can be put in that framework. Okay? Principal component analysis, basically the only thing that is looking is for energy. Okay? If your information is in the energy, PCA will solve it for you. Non-negative matrix factorization is what you're trying to do, is trying to add up things that are non-negative in order to explain a solution. That would be the matrix, the Netflix problem can be solved with that. Any recommendation problem can be solved with that. Then you have ILLE, ISOMAP, and GPLVM, that what they try to do is extend PCA to a non-linearly to a very high dimensional space and look for non-linear components in the data. And then you have Dirichlet process and beta processes, which are basically doing clustering and doing feature selection in a high dimensional space in a non-parametric way. So you need to understand the number of clusters that you have. What is really cool about unsupervised learning is interpretability. And that's what we're trying to do. Okay? We are giving them something, and we want to interpret what the solution is. Okay? And that's what we always try to do, is try to get that information out of it. This is a quote from Finale's paper, in which it very clearly explains when we're doing unsupervised learning why we're doing that. Okay? And finally, the last thing that we're doing in unsupervised learning, and I'm not going to go into this in detail, is GANs. Okay? GANs is a completely different way of doing unsupervised learning to all the methods that I've been. Okay? GANs are not interpretable. They are not giving you a latent variable that you can understand. Even though some people are trying to mimic understanding what the latent variable is, you can show that you can scramble that and still get the same model and a completely different interpretation. So you have to be extremely careful when you interpret the latent variable in GANs. The good thing about GANs, and that might be good in communications problem, is that they give you the universal simulator. Okay? Right now we're used to building our simulators our own and use those simulators to decide what do we do. Okay? What GANs give you is, no, I can observe the network. I take enough number of samples, and then I get a simulator of that network for that number of samples. Okay? And then suddenly then you can go to the lab with a simulator and generate as many networks as you want. Okay? And this is an example from the first paper that made GAN really work. That this is the paper called DC-GAN. Okay? And what you see is they start with 100 random numbers, and they map that to an image of 64 by 64 pixels. They train that with 2.5 million of bedroom images, and these are test images. And they are impressive. Okay? They really look like bedrooms. Okay? And those, they started with 100 random numbers, no structure whatsoever. Okay? Of course, if you look then up close, you have to have a weird test for that to be your bedroom. Okay? And this one is all bed, which has its usefulness, but again, not a typical bedroom. Okay? This one, these four, are these four. It's not something that I just invented. Okay? So the still GANs are not as good as representing what they are. They play with our visual system to show things that are good for humans. That doesn't mean that you're generating good images. Okay? And I think Shireen talked about all the problems that they have, and she's going to solve everything. So by the end of her PhD, you won't have any other issues with GAN. No pressure. Okay, and then the last thing that I want to go is a little bit talk about reinforcement learning. And again, like I don't know anything about reinforcement learning, let me use the Incredibles for that. And I know that you prefer watching the movie, but hey, I'm here too. Okay, so basically the idea of of these two clips is that it basically shows you what the problem of reinforcement learning is. Okay. Now you no longer have a data set that we had in the other two issues. You have an environment, and you're trying to learn how to act in that environment. So the first time that the machine, and in this case we are in the machine, we are rooting for the machine, not for Mr. Incredible, encounters Mr. Incredible, he doesn't know what that jump is. He gets surprised, and then he gets kicked in the face. The next time around that he sees that he's doing exactly the same thing is, oh, I need to do something, not just wait and see. And he decides to move one of her arm and push him away. Okay? And that's the environment in which the machine is learning. So when you're doing reinforcement learning, you have an environment and you have an agent that is trying to learn. The agent observes the environment, or partially observes the environment, and from that environment, it needs to decide what to do in that environment. Okay? That action will change the environment and will give him a reward. Okay? In the first one, the reward is that he's being kicked on the face and the machine almost got broken. Okay? But it didn't. Okay? And then the agent in the next time around, it goes through that. This is what is called a Markov decision process, and the optimization of the agent is fine given a state, a set of policies, and which is the optimal policy for each one of them. The solution to this problem in general is the Bellman equation, and what we've been doing right now is solving these things using deep neural networks. Okay? Probably the most interesting case in which reinforcement learning was used is for AlphaGo, okay? And all the subsequent things that they've been doing and the Atari games. But the AlphaGo is a very interesting problem because they were trying to solve AlphaGo as a regression problem. Okay? They weren't trying to use reinforcement learning at the beginning. What they did is they took every game of Go that was out there and they trained a deep neural network. And when they finished feeding everything that was out there, it was an okay player. Not that I know how to play Go, but that's what they say. And then what they say is, well, given that it's an okay player, let's work on self-play. Okay, let's play that machine against each other with two different networks. Let's see if you get better at it. Okay, and that's the way that they train AlphaGo in the first time. And they had okay. And this is the last slide. I'm even gonna finish on time. And this is something just to remind all of you of where you are, okay? This is from Conway, who is an entrepreneur in New York, in which he tried to show the different aspect of what being a good data scientist, a good machine learning is, okay? And that's basically, that's where you should be. And this is the main problem that we have, okay? By hacking, he means coding. He's just trying to be funny, okay? He might not succeed, but that's what he means, okay? So usually what we see is traditional research, and that's where most of com research has been, is people with very good background in math, very good background in stats, together with a very good knowledge of what communication systems are, okay? And we make both of that in order to do traditional research, okay? And this applies to biologists, this applies to any domain scientist. Machine learning basically is adding to the people that know math and stats, coding skills, in order to be able to use these computer programs, but also be able to understand what is coming out of that. Okay? Being able to solve the three of them is what will put you into a data scientist, or in this case, somebody that can solve machine learning problems in communications. Okay? What he calls the danger zone, and this is very important, is where most of you as a student end up when you're teaching these classes. I mean, when you go to these classes, people complain, oh, I thought this was a deep learning class, not a math class. Okay? The danger zone is basically, oh, I'm just going to use deep learning with this data that I got from this communication network because it's going to work. It won't work. Okay? And probably you wouldn't break anybody, you just wouldn't finish your PhD, but just think people using these things in finance without knowing anything about math and of stats. Okay? So by danger zone is that's where you don't want to be. You don't want to be the one that learns the new TensorFlow, or the new Theano, the new code that is out there, apply blindly to data without knowing what you're doing, because you're not going to solve anything, and you're only going to shoot yourself on the foot. Okay? Thank you. That's it for now.